Okay, so we're starting section 11.2. Again, it's more chi-square testing. This is, as you can see, still categorical data that we have in the example down here. But if you think about it, I've got two variables that are categorical. So we're trying, this is sort of like the correlation and regression discussion when we were trying to decide if two quantitative variables had a relationship. The example we did in class was we were looking at automatic weapons in a city and the murder rate for that city. And looking across multiple cities, we saw a relationship between those two variables. Here, I'm doing the same thing. I'm looking for relationships between two variables, but they're categorical now. So let me go ahead and just read. So it says, in our previous lesson, we learned to use the chi-square distribution to conduct a goodness of fit test. In this lesson, we continue with chi-square testing in a special test for independence. And independence is just another word for saying that there's no relationship between two variables. Okay. The context is marijuana and politics. Love to mix those two topics. The data used in this problem are based on the article Attitudes About Marijuana and Political Views. I had to look pretty hard for data on this, so you may see this is from 1973. So that's pretty old. But those were the 70s, just after the 60s. And those of us alive during that time remember that pot was pretty popular back then, but with a certain group. They may be popular with the same group now, I'm not sure. From a random sample of 270 adults, the following frequencies were observed regarding marijuana use. To a table below is missing several values. Okay, so you got the political views for liberals, conservatives, or people who have no idea what they are. I wonder if they're the big pot smokers, not sure. You got the never smokers, rarely smokers, and frequently smokers. And I didn't bother putting in information about what it means to be, rarely smoker. We'll just leave it and trust them to have some sense of what these mean. One of the things I did here when I put in the table is I left a bunch of values blank, and that was to make a point. Okay. So let's see if you can pick out what I was getting at with the blank values. So it says, we want to investigate whether the variables political views and smoking frequency are independent of one another. What's the explanatory variable? I actually don't know this. We always say the explanatory variable explains the other variable. So does your political views explain how much you smoke pot? Or does your pot smoking frequency explain your politics? I don't know. That's what I said. This is a matter of opinion, okay? So I'm going to say that it's my politics, because this is more of a personality thing. And it's your personality, I think, that sort of drives whether you make decisions like this. So I'm going to go ahead and say politics is explanatory. But I couldn't mark you wrong if you had said the opposite. And my response variable will be pot smoking frequency. Okay, there's not a right answer on that part. You can switch the answers. Okay, you think they're independent or dependent? What do you guys think? Do you think one group is more likely to smoke pot over another? If they are, then you're saying that the one variable depends on the other, so they are dependent. What do you think? I have my own opinion. I want yours. Again, I'll ask it again. Are the variables independent or dependent? That would mean that one of these groups, liberal, conservative, or other, is more likely to be a pot smoker than the other groups. I think they're dependent too. And I have an opinion of who I think is most likely to be a pot smoker, but remember, I've worked this problem hundreds of times over the last 20 years, 30 years. Well, dozens of times anyway. So I think they're dependent, but this is my opinion. This will be a hypothesis. Okay, and they asked me to explain my answers. Well, I'll tell you what I think. I think liberals smoke more pot. If you just think about what the word liberal means, it just means free, right? So liberals are just a little looser about stuff like that. Okay, enter the missing values in the table. All right, well, okay, so that means, think about this. The values that are missing are values I didn't need to tell you because they're not random values. Some of these values are random, others aren't. Okay, so for instance, the second you know there's 155 liberals, think of that as a sample size of liberals, okay? The second you know there's 155 liberals, I can tell you how many never smokers there are, how many rarely smokers there are, but I don't need to tell you how many frequently smokers there are. That's not random. So let's just go ahead and compute it. Looking for the calculator I just grabbed. So take the 155 liberals and subtract the ones you know. Okay, anybody? I got 24. Then with the conservatives, take the 55 that are there, subtract the ones you have, the 43 never smokers, and the 9 rarely smokers. And I think you get 3 conservatives that smoke frequently. Okay. Now we have to go in columns now, vertically. The never smokers, there are 173 of them in the sample. If you subtract out the liberals, 96 of them, and the conservatives, you get the people that smoke pot so much they don't know what they are. There's 34 of them, I think. Yeah, that seems right. Then the rarely smokers. Oh, no, these are never smokers. I am so ashamed of myself. They know exactly what they are. They don't know. I'm shutting up. 53 in the next category. 35 rarely smokes, subtract them out. And 9, sorry, 50, I can't get this right. 35 liberals, 9 conservatives. And so I got 9 who don't know what they are. Okay, and then the frequently smokers, these guys are smoking all the time. 24 of them. Take out 44 of them. Okay, take out the liberals, there's 24 of those. Take out the conservatives, 3 of those. And did you guys get 17? Yeah. So and so to me that's an interesting number because these guys are frequently smoking pot, and it's the only number that goes up as you go down the rows. Most people know what they are. If you're a never smoker or a rarely smoker, most people know they're either liberal or conservatives. But when you look at the people that frequently smoke pot, there's just a ton of them. The numbers go down until you get to the others, just a bunch of them that they don't really have a sense of whether they're liberal or conservative, and they happen to be frequent pot smokers. So to me, that's interesting. Anyway, we filled in the missing values. Okay, let's get deeper in. It says treat the row and column totals as constants, meaning they're not variables, and the observed frequencies as values that vary from sample to sample. Every sample of how many people are here? 270 people. So every sample of 270 people, think of all these values in the table as just random observations. Well, they're not all random though, are they? Once you know the 270 people, these values all come out randomly, but some of these can be determined by these totals here. So the ones we filled in are not the random ones. It's the ones that I gave you, that I had to give you. These 4, I had to give you, and then the rest can be figured out. So really, there's only 4 values that can vary randomly in this table. The rest of them are sort of predetermined. So it says, with the values originally given in the table, are the values you entered free, independent variables, or are they dependent? Well, they depended on the other values. Okay. If the degrees of freedom and the observed frequencies are O, and the number of free independent observations, how many degrees of freedom are there amongst the observed frequency? Again, there were 4 values I gave here. Those are the random ones. The rest of them were dependent. So there are 4 degrees of freedom here. Okay, those could be anything, but the other values couldn't. They had to be the ones we wrote in. Okay, so if a two-way table has R rows and C columns, we have to make a rule for the degrees of freedom. Okay. So there are R rows. So here R is 3. There are C columns. I'm seeing I can squeeze this in. Okay, so C columns. C is 3. I don't have to give you the last column or the last row. Okay? The random values are the ones that aren't in the last column or the last row. So the last column doesn't count, and the last row doesn't count. So it's really only 2 by 2 of data that's random in a 3 by 3 sort of matrix of values. Only 2 by 2 are random. So you just don't count the last column and you don't count the last row when you count degrees of freedom. And you do R minus 1 by C minus 1. Okay, so if you're doing 3 rows minus 1 times 3 columns minus 1, that's 2 by 2. So that's 4 degrees of freedom. That's how we'll compute that. Okay, so here's your formula. It's R minus 1 times C minus 1. That's a, what do they call that? A widow or an orphan? That should have been on the previous page. Okay, any questions? So that's the first thing that makes this different from the previous hypothesis test, is it just has weird degrees of freedom. Okay? We've got all our observed frequencies. Now we need to figure out the expected frequencies. So that's the next discussion. It's, as you can see, the expected frequency will still be n times p. But what's p? So p is a proportion, but it also stands for probability. So you can see there's a probability discussion here. Here we go. Now we understand the degrees of freedom in a two-way table. It's time to think about a hypothesis test. This test is similar to a goodness of fit test already discussed, but the degrees of freedom are different, as we discussed, and the expected frequencies have a special formula. We're conducting a test for independence. That will be the null hypothesis. So I may as well put that down here. The null hypothesis will be that the explanatory and response variables are independent. Okay. So It's asking, are political views independent of marijuana smoking frequency? To conduct a goodness of fit test, we construct expected frequencies based on the assumption that these variables are independent. That's the null hypothesis, as you see here. Okay. If events A and B are independent, then the probability of A and B is the probability of A times the probability of B. We did that back in chapter 4, I think. Okay. Suppose A is liberal, meaning political views, and B is never smoke. If we pick one of these people at random, then the probability of being a liberal who never smokes, both a liberal and never smokes, is the probability of being liberal times the probability of being a never smoker, but only if the events are independent can I use this rule. Okay, you multiply the probabilities only for independent events. So this assumes the null hypothesis is true. Okay, 155 liberals out of 275 people, 173 never smokers out of 270 people. Multiply the probabilities and you get 0.3678. That's the probability of being a liberal and never smoker only if the variables are independent. Okay, this is a proportion of people who should be in the category. 36.8%, sorry, 78% should be in the category of liberal and never smoke. If this is P, the probability, then the expected frequency is N times P. Okay, that's 270 times 0.3678, which is 99.3 people should have fallen in that category. Again, that's the liberal never smokers. How many were in the category? 96 people. Okay, there were 99.3 expected if the variables are independent, and we got 96. That's really close. Okay, so it says the expected frequency is actually quite close to what was observed, which is 96. Okay, for this event, the null hypothesis of independence seems to lead to a reliable prediction of what actually occurred. The prediction was 99.3, the observation was 96. Keep in mind, this expected frequency is computed based on our null hypothesis that assumes our variables are independent. Look once more as we backtrack through the computation we just performed to compute the expected frequency. So the expected frequency was N times P. Okay. N was 270 and the P was this 0.3678. Okay. Now the 0.3678 was this computation, which we did up here. Okay. So you see the 270 being multiplied by two fractions that are both over 270 here. And you've entered the 270 3 times in the computation, so and two of these will cancel, right? So really, there's a simplified version of the expected frequency, which is 155. That was the number of the liberals here, times 173, which was the number of never smokers. Let's double check that. 155 and 173. 155 was the number of liberals. That's the row total for the liberals. Okay. The 173 was the column total for the never smokers. Okay, the total number of never smokers. So you're doing the row total times the column total, and then the 270 that you have to divide by is the grand total. Okay, so you can see this down here. The expected frequency is row total times column total divided by grand total. And that's sort of the easiest version of the formula, and that's based on the multiplication rule for independent events. So this expected frequency should only be accurate when the events are independent. And again, this is a test for independence, and we're trying to see how good the expected frequencies fit to the observed frequencies based on the null hypothesis in this goodness of fit test. Okay, so we're ready to conduct a test for independence using a two-way table. We want to test if political views are independent of marijuana smoking frequency at a 1% level of significance. So the hypotheses for the test are null hypothesis, the explanatory and response variables are independent. Alternative hypothesis, the explanatory and response variables are dependent. So there's no variables, there's no Greek letters, You just write these sentences out for the null and alternative hypothesis. Okay, so here the null hypothesis would be just that pot smoking frequency is independent of political views. So if I can spell. Okay, and the alternative, I'll just write they are dependent. How about these variables are dependent? Okay, any questions about all that? So remember, with correlation regression, we were trying to find out if two variables correlate. And we used R, the correlation coefficient, to measure that. So when two quantitative variables correlate, that was the chapter 10 hypothesis test. This is two categorical variables. We're saying they correlate or that they are dependent. Kind of the same question. Okay. Correlation is just a slightly different concept than dependence, which I'm not going to go into. Okay. So it says this test for independence between bivariate categorical variables it requires that data be summarized in a two-way table. Row and column totals should be computed so expected frequencies can be computed next. Expected frequencies are computed with this formula. As with any goodness of fit test, we require that each expected frequency is at least 5. So that's what we did on the last lesson. And the table below gives the observed and expected frequencies in bold print. So we have to enter the expected frequencies below their corresponding observed frequencies. And the first value that we already computed above is already entered, and it looks like we're going to round this to one place after the decimal just to save our sanity. Okay, so we have to do this next value in the table. Okay, so I'm going to draw an arrow to it and say this expected frequency is going to be row total times column total over grand total. Okay, so that'll be, so the row total is the 155 times your column total. That's different this time, it's 53. And the grand total stays the same every time, 270. Okay, so you get an expected frequency there. Okay, maybe get to like, yeah, that's what I got to, 30.4. I'll put it down below here, 30.4. Okay. So this next one, same formula, different values. Okay, so the row total is still 155, but now the column total is 44 over 270. Okay, so I got 25.3. A lot of rounding. It's kind of throwing our hands up at the precision because it's just so much to do. I think I'll do one more this way. So going down to the conservatives, the expected frequency is row total. Now it's a different row total. Now we got a 55 here. Times the column total. There it's 173. Okay, and then over 270. Okay, so maybe at 35.2. Yeah, thank you. Okay, so I think that's enough showing work. Why don't you guys just take a little time to fill in the rest of this table? Okay, any questions about this? You guys agree with these numbers? Yeah, okay, great. Thanks, Andreas. Okay, so the criteria, remember, is that each expected frequency that you just computed has to be greater than or equal to 5, and I think we're seeing that. E, greater than or equal to 5 in each category. So we're going to say yes on that. Okay, any questions about this? All the expected frequencies has to be at least 5. This is the NP and NQ thing. But again, it's a little softer here. We don't have to be greater than or equal to 10. We have to be greater than or equal to 5 just because we're making it easier on ourselves. A lot of categories, right? The data gets really spread out. And the more categories you are, you can see the numbers aren't that big. We get a 9 in one category. So if we had required 10 in every category, that wouldn't have worked here. Okay, but it's been shown that the test works pretty well if you allow it to go down to 5, I guess is the gist of it. Okay, any questions? Okay, now remember we're working on this statistic here, and you know, we know the degrees of freedom. We've done that, and as before, it's always right-tailed tests, so we've done that. So we have this O minus E squared over E computation that could be computed for every category, and so this is what we're stuck with here. So I'm just going to start copying these numbers over. Actually, I'm going to grab all of them at once and start putting them in place in the table. I have the table going vertically in columns. So the columns just kind of get put in. So these are the values we had. And the first column of numbers goes here and here like that. Second column of numbers goes like this. And then the third column. Okay, so those are the E's. Go ahead and get that in. And then looks like on this part, we're going to do 4 places after the decimal. Okay, fine. So we have to do the O minus E squared over E computation. So the first one, you have to do 43 minus 30, oops, 43 minus 35.2 squared over 35.2. And again, we're going to do 4 places after the decimal now. It seems a little odd to me to be so precise after rounding so much before. But here we go. Nobody to blame but myself. So I get 1.7284. Okay. You guys agree with that? Okay, thank you. Okay, so the next one I get 0.5042. And when you square, these should all come out positive. When you square a negative, it comes positive. You don't even need to worry. Just if you see negatives, just make a positive once you subtract, okay? Everybody get 0.3 on this one? I'm nervous about that 0.3. Yeah, okay. you guys get 4 for this one? Just exactly 4? No? Yes, yes, yes. Thanks, Wenjing. This one's big, so it's a 5.2898, I guess. Okay, so before we add them up, do we have, I'm asking for one more confirmation with all these numbers. Agreed, fantastic. So add them up. Don't forget the first one, the 0.1097. It's easy to overlook. Not horrible test. Same thing on this one, guys. I'll give you, if I do this on the final, I'll give you most of these. So I'll only make you do a couple of them. $13.3594, also what I got. Thanks, Wenching. And so that's the sum of O minus E squared over E. I got a little mistake here, so I'm fixing it. There you go. And it comes out to be 13.3594. So that, to me, seems really big. Chi-square statistics can get big because you're, remember the definition, you're adding up squared z-scores, and the number of them is degrees of freedom. So if the degrees of freedom is big, then you're going to add up a bunch of squared z-scores, and it's degrees of, that many z-scores. So, let's say they were all around 1, and if there were 50 of them, then your chi-square statistic might come out as big as 50. So these can be big. It just goes up with the degrees of freedom. This only has 4 degrees of freedom, so that seems too big to me. But okay, any questions? Okay, again, the degrees of freedom, if you remember, there were 3 categories of politics, -1, which is not random, and then there were 3 levels of pot smoking, -1, which is not random. So this is 2 times 2. And we already knew there were 4 degrees of freedom. Okay, so the critical value they want us to plot here. Okay, so this is from table A4. 4 degrees of freedom, got to look up our alpha. I don't know. I think it was a ways down. You don't see it? That 1% level of significance. Man, I did not make that easy. Okay, so it's got to be there somewhere, unless I forget, and then that's not good. Okay, so our alpha is 0.01. And so here I go to that table. 4 degrees of freedom, 0.01 alpha, table A4. A little different from the last time. 0.01 alpha, 4 degrees of freedom. So we'll go all the way down to that last column. Okay, so that's actually really big. This is just kind of a measure of how much variability you'd expect in squared z-scores with 4 of them added together. We expect 99% of the time we wouldn't get any higher than 13.2767 if the criteria of the hypothesis test are satisfied. Okay, 13.2767. Oops, wrong one. I'm working on it. Okay, any questions? Now we got 13.3594. That's really close. Okay, so the test statistic is going to be just a little bigger than that. So I'll say it is in the tail. So you can reject the null hypothesis on this one. Okay, but now it wants the p-value. So I don't know how, but somehow I'm kind of marking down the test stat, which was the 13.3594. And then I'm just going to try and sort of shade a little sliver of the tail here. I don't think you're going to see anything. You know what I'll do is I'll do it with a green pen. So I'm just going to do some dark, wrong color. Like this maybe. So there's the p-val, super skinny. Okay, remember it's 4 degrees of freedom and 13.3594. I'm going to pop back to Desmos. Change the degrees of freedom to 4 and change the chi-square to 13.3594. I screwed up, hang on. It doesn't look that great on an iPad, but it's okay. And you see the p-value there is 0.009647, and if you look, you can zoom in on this tail. It's shaded, but it's super skinny. Okay, 13.3594. So the p-value is 0.0096, we'll say. Real close to 0.01. 0.0096. So that's less than alpha. Okay. So the p-val of 0.0096 is less than 0.01. This is alpha. And I may as well add that the test statistic is in the tail. Past the critical value. So that means we reject the null hypothesis and support the alternative. Okay. And so the conclusion, yeah, support H1. H1 that said that the variables are dependent. So we sort of claimed that in the beginning, that the amount of pot you smoke depends on your politics a little, and when we say they're dependent, we're saying the relationship between the variables is not cause and effect, it is one of predictiveness. So if I knew your politics, I could predict the likelihood of you being a pot smoker, and that would be better than a random guess. knowing your politics would help me to determine this likelihood. Okay, any questions? It's not saying you'd be exactly right. You wouldn't be able to say, yes, you're a pot smoker, but you would be able to say, well, knowing you're a pot smoker helps me understand how likely, knowing your politics helps me decide whether you're likely to be a pot smoker. So the data support the claim. That pot smoking frequency depends on political views. So I would say, I'm just to remind you about this, I'm adding the relationship is predictive. Not cause and effect. So always want to remember that. You can't make conclusions about cause and effect until you do that controlled experiment. No, nobody's going to do a controlled experiment. It's impossible on something like this.